All righty. Who's got a question that needs answering? All right, if nobody has any questions, I guess we're done.
I've got a question.
All righty.
Can we go over, so whenever you look at both exams, there's a question whenever it talks about the graph. Like there's a graph and it shows you, I believe it's time over positivity. Can you go over like your steps and how to solve those kinds of problems? Can we start with the fall exam?
Fall, let's see, health tests. Yeah, I'm not. So the fall 2019 exam, let me pull that up real quick. And then you'll need to direct me to whatever question it is you're asking about, because I'm not familiar with what you're saying. Hold on.
Yes, sir. Let me go ahead and pull up to.
I don't care about OneDrive, go away.
I think he's referring to number 13 on fall 2019.
All right, let's restart my PDF annotator software because it is locked up. Discard.
That's correct. Question number 13 on the fall exam.
All right, so can you guys all see it? Share my screen properly and stuff.
Yes, sir.
We can see it.
Cool deal. All right. Alrighty, so you're given the energy absorbed by a circuit element and you want the power. So what's the relationship between energy and power?
Power is a derivative.
E is equal to dW by dt. All right, we want it at 8.732. So that means we're going to be looking at the slope over this section, right? So the change in work is 2.5 millijoules. The change in time is 1 second. So the power is 2.5 millijoules per second, or 2.5 milliwatts. There we go. Was that an adequate explanation?
Where did you get the dW, the derivative of work, 2.5?
This point, hold on. Go away. I'm not talking to you students. There's a pop-up thing on my screen that I don't know how to make it leave. All right. So this point is at 2.5. And this point is at 7, 0. The change in y is 2.5.
All right, I see. Thank you.
Yep. Next question.
Sir, for in-class assignment number 5, I was curious about what was going on with D, the homogeneity and additivity properties.
I'm 99% sure there's a video up on YouTube right now explaining literally just that. So go
Wasn't sure
watch.
where the 0.6 came from.
All right, let me pull it up. In-class assignment number 5. So all right. So you're not sure where the 0.6 came from. All right, so in the problem statement here, the schematic diagram, we're told that we have a 5-volt source, right? It's literally right here. And part D says we have a 3-volt source, which means we're scaling that voltage by a factor of 0.6 because 3/5 is 0.6.
Oh, so when you're replacing the 5-volt source with a 3-volt source, you do 3/5. So, but with the other one, it's just 2.5/1. So it didn't look like there was any change.
But there was a 2.5 scaling factor, so that's a change.
Right.
Notice also that the positive polarity, it says, is on bottom. So that's where the negative sign came from as well. So when we're doing part D, we are scaling the voltage by a factor of negative 0.6 because we're changing the 5 volts to 3 volts and we're changing the polarity. For the current, we're changing 1 amp to 2.5 amps. So there's a scaling factor of 2.5. The direction is up, and so is this direction. So that's why we don't have to change the sign or anything.
Okay.
Next question.
And for number 6 on exam 1, I was wondering
Which year of exam 1?
Fall 2019.
All right.
Where did the negative sign go?
So the electron beam in a television picture tube carries 10 to the 15 electrons per second. Where electrons have a charge, the voltage necessary to cause the picture tube to absorb 4 watts of power. All right, so Jack Foyle, can you please mute yourself because it's the background noise is driving me insane. All righty, so let's see what we got going on here. We have current and we have power, right? Okay, so the reason why I say we have current is because we have the charge of an electron and the number of electrons per second, right? So our current, I, which notice is in the opposite direction of the charge Q here. So if the electrons are moving to the right, positive current is moving to the left, which I think is probably where the negative sign happened. So I is going to be, let's see, positive 1.6 times 10 to the negative 19 coulombs times 10 to the positive 15 electrons per second. So that's 1.6 times 10 to the minus 4 amperes. V is power divided by current. So that's 4 watts divided by, let's see, 160 microamps. If I did my math right. Is 25 kilovolts, yeah. So if you're wondering where the negative sign went, it's because this current I is opposite the direction of movement of the charges Q. And that's true always because Benjamin Franklin screwed things up in 1750 something, I believe. And you guys covered that actually in the first day of Engineering 120.
So essentially, it started off as negative 1.6, but because it's in the opposite direction, that negative sign canceled out.
Right. So the charge that we know of is really what the charge, or what the, excuse me, the current that we know is really what would be happening if protons were moving, but protons don't move, they're fixed. So if we're looking at electrons moving, where electrons have a charge of negative 1.6 times 10 to the negative 19, then what we are observing is that 10 to the 15 of a charge of positive 1.6 times 10 to the negative 19 is establishing the current in our cathode ray tube here.
So if the charge had been positive 1.6, would the answer have been negative 25?
So it depends on the direction that the charge was moving. So if we were able to fire a proton beam to the right, then our current would also be directed to the right. Right. So that means that the current would be flowing. So in a case like that, the current would be, let's see. So if this charge is positive, then this current is also positive, which means it's flowing out. Hello.
I think you're back, sir.
Yep. So what I was saying is that if the charge is positive and directed to the right, the current is also positive and directed to the right, which means that the tube would be supplying power to the battery, not the battery supplying power to the tube, based on the indicated directions and stuff in this diagram.
And then that would make the power absorbed negative.
Right, so the voltage necessary to cause the picture tube to absorb. So based on, again, the assumption here that the charge is positive and the current is positive, the picture tube, absorbing 4 watts of power would make the battery. So the charge is positive and directed to the right, the current's positive and directed to the right. Based on the schematic diagram here, the current is flowing into it's flowing out of the negative polarity terminal, which means it's flowing into the positive polarity terminal of the battery. So the tube would be supplying power to the battery as opposed to the opposite case that we have right here. It's just simply using the passive sign convention to figure out whether or not things are supplying or absorbing.
All right, so that means that we just assume the left side of this diagram is where the negative sign is.
The negative sign is coming from the fact that the current is moving in the opposite direction of the charge.
All right. Because I just mean like the polarity is what I mean.
The polarity of the battery is established in as much as the long terminal is always the positive and the short terminal is always the negative.
All right.
Next question.
I've actually been having a issue when I'm doing, I guess it's combining voltage sources or doing KCLs and stuff. I end up, no matter how I do them, I end up with a negative answer. And it's of the correct number, but I get the negative version of it. So I know I'm doing the math correctly. I just don't know where I'm getting those negatives. Do you have any idea where I could be doing that?
Do you have a specific problem that we could look at, or do you want me to make something up?
Can you repeat that?
Do you have a specific problem that we could look at so that I can help you, or do you just want me to make something up?
If you can just make something up, that works too. I don't have.
All right. So let's first address you getting the wrong sign when combining voltage sources. That's something that you said you were having an issue with. So let's say that we have an 8-volt source connected to a 3 ohm resistor connected to a 2-volt, like so. So the 8-volt source and the 2-volt source are of opposite polarities, yes or no?
Yes.
Okay. So then a equivalent representation of this circuit would be 6 volts connected to a 3 ohm resistor, like so, or the 3 ohm resistor connected to so let's see. So the is all about following Kirchhoff's voltage law, right? So let's see what happens if we follow it one way versus the other way. Actually, I think that'd be a better thing to do. All right, so here's our current I. We don't really, we're just direction that it's going to be flowing clockwise around this loop, right? So if, dang it, if we apply KVL, we have -8 volts plus 3 ohms times I plus 2 volts is equal to 0. And so we can see that the voltage drop over our resistor, which is just 3 ohms times I, where I'm assuming this polarity, to 6 volts, right? So if we have, damn it, if we have our resistor like so, 3 ohms, positive polarity, negative polarity, then what we should have is a 6-volt resistor, or excuse me, a 6-volt source, positive polarity on top, negative polarity on bottom. Now, let's leave the polarity of our resistor the same and follow the current in the other direction. We would see -2 volts minus 3 ohms times our current I plus 8 volts is equal to 0, which is still going to give us the exact same thing. 3 ohms times I is equal to 6 volts. So we get that exact representation, as well as changing the direction. All right, so now we have -2 volts plus 3 ohms times I plus 8 volts is equal to 0. When we do this guy, we're going to have 3 ohms times I is equal to -6 volts. So in this case, let's be clear here, this is how I is going. And in our third case down here, so the current is flowing into the positive polarity terminal. So whether you get a positive number, and in this case, we would likely find out that the current I happens to be, well, it has to be negative for this thing to work out. So it's all about following Kirchhoff's voltage law around these loops and then using the polarities of your resistors to figure out what the polarities of the voltage should be. I mean, 8 minus 2 is 6, 2 minus 8 is negative 6. You can come up with either of these circuits and be correct depending on what direction you choose for your current, in addition to what polarity you choose for the voltage drop over your resistor. So the biggest thing that I would check, so what I was originally going to draw, and it might be, no, that would have wound up with the exact, it still would have been positive 6, yeah.
Okay, what I'm thinking I might be doing is there's some of those problems that sometimes they like throw in negative numbers and stuff, and I don't ever flip the polarity. I just try to work it out like that, and sometimes I think I just end up with the negative is probably what it is.
Yeah, so in the overwhelming majority of problems, if you're given a source that has a negative value, if it's a voltage, I would just go ahead and flip the polarity. And if it's a current, I would go ahead and flip the sign. In my mind, having all those extra negative signs, I know they make me make extra mistakes.
So on voltages, obviously you flip the plus and minus, and on a current source, can you just flip the arrow?
That's exactly right.
Okay, just wanted to make sure because I've been kind of scared to just do that without asking. So okay.
Yeah. Now, with regards to you getting the wrong number or whatever, or the wrong sign on your KCL equation, following the convention correctly. So there are 3 different formulations of Kirchhoff's current law, and they're all related to each other. One of them happens to have a factor of -1 thrown in there. But when I was working homework 3, I think it was problem 1. I don't remember what day I did that off the top of my head, but I went through, I think it was with the second, with the group B students, I went through and we worked that problem just messing with the currents, like having all the resistor currents down, all the resistor currents up, some of them down, and you get the exact same equation every single time, as long as you're consistently applying your Kirchhoff's current law convention. And what I mean by that is either saying everything going into this node is positive or everything coming out of that node is positive, as well as properly applying Ohm's law. And Ohm's law over a resistor effectively boils down to, if the current's going into the negative polarity terminal, you need a negative sign. And if the current's going into the positive polarity terminal, it needs to have a positive sign. So I think that would be a very good place to go review those rules of applying KCL when the currents are every which way. Because I went through every permutation I could think of with those students to try to help reinforce that if you're applying things correctly, it doesn't matter what signs you choose. It's entirely arbitrary, or what directions you choose for currents and things like that. It's entirely arbitrary as long as you're applying KCL correctly and using Ohm's law correctly.
Okay, thank you.
Yep, next question.
Could you work out number 12 on the same pretest that we were on? Or practice test, I mean. Exam 1, fall 2019.
Number 12, let's find it. Time varying current through a circuit element is given by that mathematical expression. The initial charge is blah, the current on the element is blah. All right, so charge as a function of time, that looks like a G, not a Q, excuse me, is the integral from some point in time where we know what the charge is to some later point in time of the current with respect to T prime dt prime, where these T primes are simply dummy variables. They do not mean take the derivative or anything like that. I just have the variable t in my limits of integration, so they shouldn't be inside my function as well. All of this integral plus the initial charge at the time that we know. So in this case, we're going to be, let's see, we know the charge at t is equal to 0. So 0 is the lower bound of integration. We're looking for the charge at 1.528 seconds. So 1.528 seconds is our upper bound. We are integrating the function 2t to the 4th power minus 6e to the minus 3t plus 8 amps. And all these t's should technically be primed. Doesn't particularly matter. Plus 4c. 4c, 4 coulombs, it says the initial charge is 4 coulombs, which means the charge at t is equal to 0 is 4 coulombs, so that's why I'm putting it here. So at this point, you could literally put it in your calculator, or do you want me to do the calculus by hand? I'm fine either way.
I'm good. Thank you.
All right. Next question.
Can you hear me?
Yes, ma'am.
Okay, on exam 1, the winter exam, number 24, how do you know what VX is equivalent to?
All right, let me find that real quick. The winter exam. What problem was that, please?
Number 24.
Where am I at? All right. Okay, so let's see. How do I find Vx? All right. Well, not specifically how do I find Vx, but you're asking like, it's not super obvious as to what element or something like that you're looking for the voltage drop over. Is that correct?
Yes.
Okay, so that whole node is connected to the negative polarity terminal. This whole node is connected to the positive polarity terminal. So from that, plus, minus, right, silly, Vx. It's a voltage drop over the 3 ohm resistor, positive polarity on bottom.
And that is because they're in parallel, right?
No, it's from the definition of voltage. Voltage is defined as the difference in electric potential between 2 points or 2 nodes in a circuit. So Vx is defined as the difference between this bottom node, or the maroon node and the green node, which is the exact same thing as the voltage drop over the 3 ohm source, or excuse me, the 3 ohm resistor, positive polarity on bottom. So, I mean, saying the voltage is in parallel with an resistor it's across is kind of strange, which is why I said no. So I would look at it from literal fundamental definition of voltage.
So if I made the maroon node ground, VX would just, can you hear me? Sorry, there's a train.
Yes, what's up?
So if I made the maroon one ground, then VX would just be the 0 minus VA, which would just be negative VA.
So you
Or
called this guy VA,
V1, whatever
VB,
you,
and then this guy VC or something like that?
yeah.
And bottom as ground, then you are correct. Vx would be negative VA.
Okay, thank you.
Next question.
Something I found interesting about one of the resistance questions, specifically the one from the winter exam, number 16 and 17. Something I found interesting is that the 4 is completely ignored because both sides are on the same node. Does that mean that it's a short circuit?
It's sorted out by this circuit right here.
Excuse me?
The 4 ohm resistor is shorted out by
Okay.
the short circuit that I just circled. But yes, if a particular circuit element has the same node connected to both terminals, then that means it's shorted out.
I see.
All right, next question.
While you're on this question, would you mind showing us how you would simplify that circuit? Like how you would go through going from A to B?
Sure. So let me get some different colors and all that kind of jazz out here. Let's see. All right, so that is not this. So that's one big node. Node C. Now we could hopefully see that B and D represent the exact same thing. Here's A. Alrighty, so the different paths from A to B. So let's label these other nodes real quick as well. All right, so that's A and that's B. Let's call this guy C. Nope, that's dumb because this other guy is already C. Let's call it E because that's something that I haven't yet used. That looks terrible. Alrighty, so to go from A to B, and I'll try to do this here. I'm obviously going to have to go from A to E first. There's no other path that I can take. So that means I have the 49 ohm resistor right here. Now I can go from E to B directly, right? So E to B through the 13, through the 5, or through the 34. This guy taken care of, this guy, and this guy, or I can go from E to C to D. So let's just put C here for the sake of argument, which is the 8 ohm resistor. And from C to D is through the 50 ohm resistor, or excuse me, C to B. C to D, which is also B. 50. So the equivalent resistance is 49 ohms in series with the parallel, with 13, 5, 34, and 58 in parallel. Everybody see that?
All right, maybe
he did. Maybe he didn't. There's like a teacher like walking behind. He was like staring at me.
Tristan, I think you have your mic on.
All right, so next question. I just checked and that is the right answer.
Dr. Hartman?
Yep.
Number 18 on the fall exam, or it should be the fall exam.
Okay, let's see if I can move this over. Number 18 on the fall.
So I know the solution you guys provided us they used current division, I believe twice, and I was just kind of confused about that process.
Okay, so the current division that I used was not the method that was taught in the video. So
Okay.
let me when there are exact or let's go through it real quick. Okay, so
Okay.
one way to think about this is, and this is to the person who I was talking to earlier, saying, oh, if you see a negative number, just change the sign. Well, when we do current division, let's be clear about what's going on here, because I'm about to throw in a negative sign that might be mildly confusing. So let's say that I have the resistor R1 and the resistor R2 like so, okay? I know the current that's flowing into this network, and my expectation is that my current through resistor R1 will be down and my current through resistor R2 will be down like so. So what I have right now is a 6 amp source, and let's change this slightly. Let's call it a negative 6 amp source and make the direction up. And the reason why I'm doing that is because I know then that current will split down through that guy IX and then down through this resistor R4. So from this, I can say that IX is going to be negative 6 amps, the current entering my parallel resistor network. And in the denominator, I'm going to have 1 divided by R1. So it's the reciprocal of the total resistance of this branch right here, because that current IX is going to split up and flow through R2 and R3, and then it's going to recombine and all that kind of stuff. So I need to make sure that I account for all of the resistance that the current IX sees. So that's going to be R2 times R3 over R2 plus R3 plus 1 over resistor R4. And in my numerator, I will again have this 1 over R1 plus R2 R3 over R2 plus R3. That's correct. Now what you see in the solution, and I'll do it over here, IX is equal to negative 6 amps times R4 over R4 plus R1 plus R2 R3 over R2 plus R3. That's what it shows in the solution, right?
Right.
Okay, so let's circle back around to this guy up here. So we know that let's look at just the current IR1 is going to be IS times 1 over R1, 1 over R1 plus 1 over R2, right?
Right.
Well, if I multiply this guy by R2 over R2 and this guy by R1 over R1, what I wind up having is IS times 1 over R1, and then I'm going to have R2, R1, R2 plus R1 over R1, R2, like so. So that's a common denominator, so I can actually add these fractions together. So it's going to look like R, dang it, come on, pen thingy. Technical difficulties here, there we go. R1 plus R2 over R1 times R2. I have a common, so I have 1 over R1 in the numerator and a 1 over R1 in the denominator as well. So I'm kind of running out of space here. So this is going to look like IS. So when I divide by a fraction, it's multiplying by the reciprocal, R2 over R1 plus R2. So these formulations are the exact same thing, but this method where we choose the path we don't want is only, or we choose the resistor we're not trying to find the current through, only works when there are two resistive branches in parallel. Whereas the method that we used in class, this guy right here, works for an infinite number. So I would encourage you to learn this guy and pretend I didn't use the other one because it's useful, but literally only useful when there are two resistive paths in parallel.
Dr. Hartman, could you explain why you made the 6 amps negative in this case?
So it all goes back to this drawing right here, okay? So the current flowing into the node. So I'm trying to find IX, which is the current going down, right?
Yes.
With the original drawing, I know that my 6 amp source is going to cause some current to split off and flow this way, and some current to split off and flow this way, right? And then this current down here in maroon is going to split, and some of it's going to go this way, and some of it's going to go this way. And I know that the blue and the gray currents are going to add together to be this guy, which is in the opposite direction of IX.
Mm-hmm.
So I would have a negative sign. And that's a lot of screwing around with stuff. Whereas literally, if I just put a negative sign here, I know, well, this guy's going to split. Some of it's going to flow this way. Some of it's going to flow that way. And that's why I did it.
All right. Thank you. That makes sense.
Yeah, I mean, it's just, it's going to get a negative sign no matter what. It's just way easier to justify where the negative sign comes from if I just change the sign on my current source to match the convention, as opposed to making the convention match the sign or the original direction on my current source. Next question.
Dr. Harden,
Mm-hmm.
can you go over number 35 on the winter exam?
Let's see what 35 asks us. Here at the bottom, I think. All right, 35 defines Vx in terms of the mesh current. So let's go up here and look at stuff. All right, so Vx, I'm going to assign like so. I'm going to write a simple KVL equation, which says that Vx is equal to V4 plus V38, right? If I do Kirchhoff's voltage law around this loop, I would have negative Vx plus V4 plus V38 is equal to 0. When I move Vx to the other side, I get this exact expression. V4 is 4 ohms times mesh current I4, and V38 is 38 ohms times I8.
Okay, thank you.
Next question.
On the winter exam, can you look at number 4 and just kind of explain what we should be thinking when we're doing a problem like that?
which of the following expressions relate power and energy?
Yes.
Okay, so if power is the derivative of energy, then that guy's right. And that also means that energy is the integral of power, so that guy's right. And both of those should have been covered on the first day of the first lecture of class.
Could you do number 30 on that test?
KCL for node 6. Alrighty, so let's see, where's node 6 at here? 1, 2, 3, 4, 5, 6. All right, so we want this guy, and this guy. Excuse me. So starting with the one diagonal to the left, that's V6 minus V4 over 22. Next up, V6 minus V5 over, I drew over the thing, 3. And then lastly, diagonally down to the right, V6 minus the reference, which is ground, over 7 is equal to 0. I put something down here. 6 minus 4, nope, that's it. Excuse me. Next question.
Dr. Hartman, do you mind looking at fall 2019 number 33?
Let's see, 33 is KVL for Supermesh 345. Alrighty, I'm gonna need to make this potentially smaller so that we can see all of it in one go. Three, 4, 5, right? So there's 3, it encloses that guy. So that's our path. So do I have space? All right, so let's start from down here. We see a whole short circuit, so it's going to be positive 16 volts plus 23 ohms times I3 minus I1 plus 16 ohms I4 minus I1 short circuit 13 ohms I4 minus I6 20 ohms I3 minus I8. Yeah. And then minus 10 volts is equal to 0. And knowing me, I might have ran out of room, and so I just called it 6 volts or something like that. Yeah, so the 16 minus 10 is 6. So that's where this 6 comes from. So 23, 16, 13, 20. 23, 16, 13. Yep, got all the resistors in there. Combine the voltages because the expression was literally getting too large to fit on one row on my answer thing. Is that satisfactory, Kendra?
Yes, sir. Thank you. I appreciate it.
Yep, no problem. What's next?
Could you do a number 34 on that same test?
Number 34, Vx in terms of the mesh currents. Sure, let's see. All right, so let me define, let's call this guy V20 and this guy V19. All right, so that Vx is equal to V20 plus V19, where V20 is 20 ohms times I8 minus I3, and V19 is 19 ohms times I8 minus I6. Yep, there we go. Next question.
Could you look at 23 on that same test?
23. All right, so 95% sure I did this using nodal analysis because there are 4 meshes and I didn't want to mess with things. So let's call this guy node 1, node 2, and node 3. So KCL at node 1 means we're going to be looking for this current, this current, this current, and this current. So that is negative IS plus V1 minus V2 over 20 plus V1 minus V2 over 8 plus V1 minus V3 over 6 is equal to 0. At node 2, we're going to be looking for this guy, this guy, this guy, and this guy. So starting diagonally down and to the left. Oh, and it's crap. Hold on. Starting diagonally down and to the left, we're going to have V2 over 5. And I should have specified this earlier, but my bottom node is my ground. Then V2 minus V1 over 20. Then V2 minus V1 over 8. Then V2 over 17 is equal to 0. At node 3, we're going to be looking for this guy and this guy. So that's V3 minus V1 over 6 plus V3 over 19 is equal to 0. And then solve things up. Vx is exactly equal to V3. Iy is V2 over 17.
Dr. Hartman, is there a particular reason why you put the ground at the bottom versus putting it in the center? Because I know you can put ground just about anywhere.
Yeah, not really. I just made sense, so I did it. But yeah, I could have put it at the top, could have put it at the middle, could have put it where node 3 is. I just chose the bottom because I'm lazy.
Got it. Thanks.
Next question.
For this one, you would just do like the systems of equations, and that's how you get V1, V3, and all that?
Yeah, yeah, so I mean, you have all the equations here, so at this point, it's just putting stuff into your calculator.
All right, sounds good.
I know you're like past the question, but on number 18, when you did current division, could you solve it using like KCL? Even though it might not be quicker, but could you solve it just another way?
So let's see. So we could call this guy node 1, this guy node 2, this guy ground, and do nodal. Yeah, so 2 equations, 2 unknowns. Nothing particularly difficult there. Ix would have been V1 minus V2 over R1. Or we could have done, call this guy mesh 1, this guy mesh 2, this guy mesh 3, and then solve that system of equations, and Ix would be I1 minus I2, and you get there. Yeah, so the reason I personally didn't do it is because I knew I could do it with one equation in current division. But you can absolutely solve this problem using nodal analysis or mesh analysis, or if you want it to take a really long time, applying Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law.
Dr.
So
Hartman, also, you know how like we have the test paper? Are we gonna have scratch paper or
3 blank sheets of paper stapled to the back of the exam, and I print the exams one-sided, meaning the back of every sheet with the questions on it is also available for you to scribble on and stuff too. So if you're concerned about having enough space to work, I feel like 3 sheets and probably the back of around 15 sheets should be enough. Did that answer your question?
perfect?
All right. Next question. Last call for a question. Alrighty, see you all this evening in whatever room I sent out in my email. I don't remember off the top of my head. I think it's 212.